Okay, hi guys. So in this video we're going to look at this differential equation with some conditions on it. So we want y to be a function that satisfies this differential equation. So y prime equals y times sine of xy times e to the negative xy, with y of 0 being some y0 which is positive, and as x approaches infinity, y approaches some L which is some constant. In this video I'll derive a approximate solution for L given by this expression here, which involves the Lambert W function. So if we just start, if y goes to L as x goes to infinity, then for x large enough, we can write y prime equals y sine of xl, because that's the limit, e to the negative xl. So this is a differential equation that we can more easily solve than the other one. So dividing through by y on both sides, we get y prime over y is equal to sine of xl e to the negative xl. Now we need to integrate this with respect to dx on both sides, and we'll lazily do this on the left to just get the natural log of y, and that's equal to the integral of sine of xl times e to the negative xl dx. So to actually do this integral, we're going to use integration by parts, and I'll use the di tabular method for this. So we'll differentiate sine of xl, and that goes to cosine of xl times l, and then again we'll get minus l squared sine of xl. And now to integrate up, we integrate e to the negative xl, and that's minus 1 over l e to the negative xl, and then again 1 over l squared e to the negative xl. We multiply the cross multiply for those terms, so we'll get minus sine of xl divided by l times e to the negative xl, and then again minus cosine of xl over l e to the negative xl, and now for this term we multiply directly across, and that just gives us back our integral, but this time negative. Now if we add this to the left hand side, so this term up here, we'll get two of them, so if we divide by 2, we'll have this integral equals 1/2 this stuff. So let's just minus 1 over l e to the negative xl sine of xl plus cosine of xl. And then if we plug this into the thing above, so I'll just scroll down a bit. So what do we have? We have the natural log of y, that's equal to minus 1 over l e to the negative x times l sine of x times l plus cosine of x times l plus some constant c. Now for the sake of just bookkeeping at this point, I'm going to rewrite sine of xl plus cosine of xl in the following way. So sine of xl plus cosine of xl, I'd like to rewrite this as some constant a times the sine of xl plus some phase shift. And now if we expand this term out, we'll get a sine xl cosine of phi plus a cosine of xl times the sine of phi. Now reading off and comparing the coefficients. So on this side we have 1 times sine of xl. Over here we have a cosine of phi times sine of xl. So just comparing, a cos phi equals 1, and similarly a sine phi equals 1. And now if we divide through, so we divide this bottom equation by the top equation, we'll have tan of phi equals 1, and from that we'll get phi is pi over 4. And applying the Pythagorean theorem, a squared sine squared of phi plus a squared cosine squared of phi, that's equal to 2, because we add these two equations squared together, and then sine squared plus cosine squared equals 1. So what we in fact have is a squared equals 2, and we want to take the positive one here, just because over here for phi we picked pi over 4. If we picked the negative one, we'd have to have a different phase shift. So now we could rewrite natural log of y as minus e to the negative xl over the square root of 2 L sine of xl plus pi over 4 plus a constant c. Now we want to take this, now we want to exponentiate both sides. So y equals, if you apply the exponential function to the c, we can drag it back out to the front for some constant again, b maybe. And then this is just the exponential function of this chunk here. Now we have two conditions that we haven't used yet. So that's y approaches L as x goes to infinity. I mean, we've technically used it, but not fully. And y of 0 is equal to y naught. I'm going to use the top equation first. You can use the bottom one if you want to, but it doesn't really matter. So have a look at this. So if y approaches L, we're going to write L equals, and now the limit as this function goes to infinity. B is a constant, exponential function is continuous, so we move inside. Now the sine function is just oscillating up and down, so we can sort of ignore it, especially because this exponential goes to 0, because e to the negative something very, very big, and negative gives you 0, so we'll have exponential function of 0 times some other stuff. So exponential of 0 is 1, that means we'll just get L equals b. So we can write our approximate function as L times this function up here. Now we still have this other condition that y of 0 equals y naught. So if we plug in 0, we'll get y of 0 equals y naught. And now directly plugging 0 in here, well, we'll just have the L times exponential of, well, here e to the 0 is 1, so we'll have minus 1 over the square root of 2 times L, and here sine of 0 L, so sine of 0 plus pi over 4. So the sine of pi over 4 is 1 over root 2. So if we have 1 over root 2 here, we can combine these two to just get a normal 2. So L equals e to the negative 1 over 2, sorry, y naught equals L times e to the negative 1 over 2L. Now this equality only really holds when y naught is large enough, but that doesn't matter too much right now. So let's move over here. So what we've derived now is a relationship between y naught and L, which is y naught equals L times e to the negative 1 over 2L. Now this isn't very useful at the moment because we want to get L in terms of y naught. So if we multiply the left side if we multiply both sides by e to the 1 over 2L, it will cancel on the right, and on the left we're left with this, y naught times e to the 1 over 2L equals L. Now if we divide everything by 2 times y naught times L, this will magically fix everything. So we'll have 1 over 2L e to the 1 over 2L, and that's equal to 1 divided by 2 times y naught. Now we can use the Lambert W function, which is defined as the inverse function to x e to the x equaling some y. So if this is true, then x is equal to the Lambert W function of y. Now applying it down here, we can see our x is 1 over 2L and our y is 1 over 2 y naught. So what that means is 1 over 2L is equal to w of 1 over 2 y naught. And now if we multiply up by the L and divide by the W function, we'll get our approximation. So it's the L equals 2 times W of 1 over 2 y naught, and then all to the negative 1 power. Now this holds for very large values of y extremely well, but it's pretty good up until about a half, where it starts to really fall apart. Okay, well, thank you for watching.